Alright, welcome to the next one. Today what we're going to be talking about, only, don't worry, I'm not going to trick you today like I did last day. We're going to be talking about Sn1 mechanisms. So Sn1 mechanisms, it's the exact same as what we did with the Sn2. It's substitution, nucleophilic, and 1, so it's unimolecular. Unimolecular, which means that the rate only depends on one of the species is equal to K multiplied by the concentration of something, and we're gonna talk about what that something is in a second. So the difference between Sn1 and Sn2, if we got Sn2 versus Sn1, like we talked about Sn2 already. We talked about, it depends on two different things. It depends on the rate, depends on the nucleophile. It depends on the haloalkane. It causes an inversion, and that's what we said, the Walden inversion. So it depends on the nucleophile and the haloalkane, which makes it the Sn2. It's a nucleophilic substitution, so we're substituting something for something else, and we get an inversion of the center. What we're going to see with Sn1 is that it depends on the haloalkane, or the rate at least depends on the haloalkane. We see no inversion, and the nucleophile in this case doesn't really have an effect on the rate of reaction. So our rate for a unimolecular depends only on one thing, and it only depends on the concentration of the haloalkane. And I'm going to show you why that is right now. So basically, we'll continue on a little bit from the last video, right? We covered primary, secondary, and tertiary carbons. So primary was where the halogen is bonded to a carbon, which is only bonded to one other carbon. Secondary was where the chlorine was bonded to a carbon that's bonded to another carbon, or two other carbons. And our tertiary was where the halogen is bonded to a carbon, and this carbon is bonded to three different carbons. I'm just going to fill this in, CH3. So just imagine they're all methyl groups. So we had, right, our primary was this carbon was only bonded to one other carbon. R just means some sort of chain. Our secondary, this carbon, is bonded to one carbon, which is the R down here, and the second carbon right here. And tertiary meant that this carbon is bonded to one carbon, two carbons, and three carbons. So he's bonded to, 1, 2, 1, 2, 3, and one other carbon. So this mechanism that we're dealing with today, we're only going to be dealing with tertiary carbons. And that's because of, in that first video I kind of talked about a little bit about the inductive effect, but we're going to be discussing that further in a second. So basically, what an Sn1 mechanism is, I'm going to draw out a reaction mechanism, then we're going to look at the differences between the Sn1 and the Sn2. So if we've got carbon here in the center, and like we said, we're dealing mainly with tertiary, so I'm just going to draw CH3, 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 and it doesn't really matter what halogen we have here. We'll just put we'll change it up a little bit. We'll be a little bit risque. We'll put a bromine right here instead of a chlorine. I'm out of my comfort zone now. So basically, This reaction is gonna happen. Like we said, it only depends on the on the halo alkane. So what Sn1 does versus Sn2, right? Sn2, we needed some sort of nucleophilic group coming in to attack the backside and push off this bromine. But in Sn1 mechanisms, we don't have that. We have, it happens in a stepwise manner. So what happens first is that this bromine actually, likes being in solution quite a bit. It's a weak base, or a weak Lewis base. So bromine is a weak Lewis base. So it can donate electrons, right? It can, but it doesn't really like it so much. It just prefers to be stable. So what happens, since it's the weak base, what can happen is that it can take back those electrons, so those electrons can move back. So what occurs is that this is a heterolytic fission. So both of the electrons go to the bromine atom. So if we were to look at the next step of the reaction, we've got a carbon with the 3 CH methyl groups around it. And we've got this bromine that just, went off. He ran away from home, right? So that this bromine just left. So of course, if we calculate the formal charges of this carbon right now, right? We've got 4, typically it has a charge of 4, or has 4 valence electrons. You minus off half the bonded. So 4, 3, 2, 1. He's got a +1 charge. He's got a positive charge on him right now. And carbon doesn't like having a positive charge on him. So of course some other type of reaction needs to occur, but we're going to talk about that in a second. But first we're going to talk about what's going on right here, right? So this, I'm going to erase up here. There you go. And basically, what that is called, this group, I'm going to keep the color the same just so you can know that they're related. This is called a carbocation. Cation meaning it has a positive charge, and carbo, that's on the carbon group, so carbocation. And what happens is that the stability of carbocations goes from tertiary, is more stable than secondary, which is more stable than primary. So that's why primary, right? Primary alkanes, or primary haloalkanes, they undergo a different mechanism. They undergo the Sn2. The tertiary is the most stable carbocation, so it can last the longest. It can survive in the solution to wait until the nucleophile can come in and attack him. So I'm just going to erase this because it doesn't really look that nice. So stability is that, a tertiary is more stable than a secondary, which is more stable than a primary. And why this is because that little bit of that inductive effect that I introduced in that last lesson is that the more carbons that this central carbon right down here, I'm just going to draw him in pink now to show that he's different. So the amount of carbons that he's bonded to, what these carbons can do is that since there's a slight difference in electronegativity between the carbon and the hydrogen, so these carbons already have a little bit too much electron density. They're not more than they're happy with. Of course, they're happy with what they have. But since they've got a little bit more electron density, what they do is they start to donate. Since this is a positive charge and he's unhappy, they start to donate, right? It's just like your friends sharing candy, right? If you've got a lot of friends around you and they all share a little bit of candy, it makes you very, very happy. If you've only got one friend around you and he gives you a little bit, you're gonna be like, come on, man, just give me a little bit more. I swear I'll pay you tomorrow. So these methyl groups, what they do is they end up donating electron density, and that stabilizes this tertiary carbocation. When you've got a secondary, right, you've got only 2 groups here donating electron density, so it's not as stable. When you've got a primary right here, you've only got 1 group donating electron density, and he doesn't want to lose too much. He doesn't want to become too positively charged either. So based off of this, they can all donate a little bit, or he can have one friend donate a lot, which will make his friend unhappy. So basically, the more groups you have bonded, the more stable it is. So then, in this situation, the next step is, of course, we're doing a substitution reaction. We need to substitute something for where that bromine used to be. And this is where you take a better nucleophile, and we're going to talk about what makes a good nucleophile in the next lesson. But, a hydroxide is a better nucleophile. Both because it's got the lone pairs, right? You need lone pairs in order to form dative bonds. You need lone pairs in order to be a Lewis base. And the negative charge basically just helps out. He's got an abundance of charge that he's willing to give away. So you draw that this bond comes in and forms. And the next step, we've got our final step right here. CH3, CH3, OH plus bromine. So the amazing thing to see about this, right? From what you guys have learned about, right? We've just converted. If you imagine we have this group right here, right? Now we can take it and we can say, okay, where did this come from? And this came from, which you guys are going to go, whoa, that's the coolest thing in the world, right? So what this came from is it came from a tertiary alkane. But then we reacted it with bromine under UV light to form the bromoalkane. And then now we've substituted it. So we've went from an alkane to a haloalkane to an alcohol now. So right, we've changed these groups, we've changed their reactivity, we've changed the intermolecular, we've changed everything, we've changed a lot of things by undergoing a stepwise reaction. We went through the first step, the second step, and the third step being an Sn1 that undergoes the Sn1 reaction mechanism. So that's basically the basics of what you need to know about Sn1. In the next video, we're going to talk about factors affecting the rate of nucleophilic substitution. So we're going to talk about what makes a good leaving group, what makes this bromine, want to leave. Because, right, if we can make him leave more, or if we can choose a group that wants to leave more, this reaction is going to speed up. We've got the rate depends on the haloalkane. If we make this group want to leave as quickly as possible, we can make this rate of reaction go a lot faster. And it's the same thing for the SN2s. If we can make a better nucleophile, the better the nucleophile we put in, the faster the reaction is going to occur. So we're going to talk about the factors affecting both SN1 and SN2 mechanisms in the next video. Hopefully this was helpful.